This was a typical catching up question from the 2019 IEB past paper. So if you read the question, it says Helen and Matthew are riding their scooters, and Matthew is at rest when Helen passes him. So I'm going to do Matthew. Yeah, I like drawing a little diagram, and this is Helen. So are they at the same point where Matthew is at rest? So his initial velocity, you can use u or vi. So vi is 0 for Matthew, and Helen passes him and she's already going, and it tells us that she's going at a constant speed of 0.37 meters per second. Okay, so we know he's 0. Then here he goes. She goes. Helen is going peacefully on her way, and after she's traveled for 1.8 seconds. So 1.8 seconds later, Matthew decides to leave, but he leaves from the exact same point because that is the point where she passed him, and he's traveling at this, and he's accelerating then at 0.91 meters per second, is what the question is telling us. He starts from 0. We already said so. When they are side by side, which the question is asking us, so always read your question first. I just jumped in because I've read it before. So side by side means they would have traveled the exact same distance, because to get here side by side, it would mean that Matthew must travel all the way to that point and Helen must travel all the way to that point. So their delta x's or their s's would be exactly the same. So we know that delta x here for Matthew must be equal to delta x here for Helen. So that already helps. We always think about the time and the distance and think which one is the same. But now let's do the time while I'm talking about it. So if we think about it, I always make it simple by saying who's traveling for the longest time, because then it puts a plus in my equation, and it also makes the math a little bit easier, like you would see later if there's a quadratic equation. So after 1.8 seconds, Matthew decides to chase Helen. So Helen was already going. So if I make Matthew's time, and that's what I'm going to do here. Say Matthew's time, t for Matthew, is x, or let's just call it t. You can use x's. I know some of you are much more comfortable with having x's in your equation, but it's t because it is a time. Let's just keep it a t. And then t for Helen, she was already traveling, so she's the one that's traveling for the longest time, is going to be t plus 1.8. I'll show you that you could have done it the other way around as well. You could make Matthew minus, and it will be exactly the same. It doesn't matter. I just like the positives because it's the maths. Now I'm going to say, fine, I know their distances must be equal by the time they catch up with each other. So I can say that delta x for Matthew must be equal to delta x for Helen. So let's think of an equation, and I think by now you know that the equation, if there's a 0 acceleration, definitely, then the equation that says s is ut plus half at squared, which would mean delta x, if you're using the other equations, equals vit plus half at squared, becomes very simple, because this last part, because a is 0, just falls away straight away. And it just becomes VI, which we know already for Helen is 0.37 T. But this is T for Helen, remember? And we already said T for Helen is T plus 1.8. Now, this T didn't have a square in it, and that's also why I'd like the plus to be there to make the math a little bit easier. Now I'm going to do this. So that was Helen. Do the same for Matthew. Same equation, because U or VI for Matthew is 0. So I'm going to also say delta x equals ut plus half at squared, but I'm not going to, so the first part falls away. So it's just going to become half a t squared, and that's going to be half, where they gave us Matthew's acceleration as 0.91 t squared. So see, if this t plus 1.8 was there, it would become a bracket, which you have to expand, and the math becomes a little bit more tricky. So the one with the square, I like to keep it clean, you can almost say. Doesn't matter though, if you're good at maths, you can do it either way. Now we can say these two delta x's are equal to each other. So let's do that. We said already Matthew, which is a half times 0.91. Now it becomes just plain algebra equals 0.37. Oh, I forgot. That's not a square. See, that's why I didn't want the square there. T plus 1.8. And now we just have to solve this quadratic equation. You're going to multiply everything out. I'm not going to do the maths in detail. Some of you know already how to do it on the calculator. I'm just going to write the simplified equation that I ended up with was 0.55 t squared minus 0.37 t minus 0.0, that's a lie, 0.666 equals naught. And then you can plug this into your calculator, or you can solve your quadratic equation, and you will get that t is equal to 1.68 seconds. But remember, quadratic equations generally gives us two answers, or t equals 0.89 minus. And sadly, we can't go back in time. So this would have been before this actually even started. And that's why we cannot use the negative time. Would be great. We could go back in time. But what if we actually worked out now? So we have worked out that t is 1.868 seconds. And t is the time that we assigned for Matthew. Always go back and check, have I actually answered the question? Because it says how much time does Helen have from the moment. So now we just need to go back and see, okay, have I actually got Helen's time? And that the answer to that question is no. I have Matthew's time. So t for Helen is just going to be the t that we just worked out, which is almost will use my negative time there, 1.68 plus the 1.8 seconds that she was already traveling when Matthew started, and that gives us 3.48 seconds. So it takes Helen 3.48 seconds before Matthew catches up with her. So sometimes they would say, how long does it take Matthew? So always go back and look whose time am I working out, and make sure that you've worked out the right one. Sometimes you have to add, sometimes you have to minus, and you will see if you actually looked at the memo for this paper that they did it the other way around, but it really doesn't matter. We'll mark any correct signs. We will mark right. So you will see that in the memo here, they actually said, okay, Matthew's time is t minus 1.8. And for Helen, they made the time t. Doesn't matter, because now when I work out the time is Helen's time. So that's fine, because that's what we wanted, is the 3.48 seconds. And you'll see that it's exactly the same as this answer that we got. I just kept my math a little bit more simple.